with a video just to open it, and we're going to jump right into it.
Thank you, Connor. So the film, the short film I'm about to show you is called The Third and the Seventh. It's by a 3D artist known as Alex Roman, and it aims to capture, as he says, architecture through the cinematographic lens. And I'm only going to be showing you a part of it, and then we'll get started with my presentation. It's 10 minutes long, so I have to keep it really short. So in case you could or couldn't tell, that video is basically a product of CGI, or computer-generated imagery. Now, in case you guys don't know, computer-generated imagery is basically just a term for anything that's basically anything that you might see in an image or a video that's the product of a computer using a 3D program. Now, and what my talk is going to be about is basically understanding this process, and that'll be there are three big parts of making, in the process of making computer-generated imagery. Those 6 parts are modeling, texturing, and animation, which you can think of as like the big 3 necessarily. And then you have lighting, compositing, and rendering, which is one of the, they're not as important, and they generally don't get as much time spent in it. But yeah, let's get started. So modeling, what is modeling? Modeling is basically the construction of the 3D geometry that makes up a 3D object. You can think of it as basically, and it's and all 3D models are built on these things called polygons. Now we all know polygons to be just shapes of any two-dimensional shapes of any with any amount of sides. And now most polygons are made of either quadrilaterals, which you can see here. Here you can see how the artist's the model is made up of quadrilaterals, which are basically 2-dimensional 4 four-sided shapes. Here's another example. And this example shows how you can actually see how this one is made, instead of quadrilaterals, it's made of triangles. So now that's interesting and all, but it doesn't really tell you how it's made. So okay, yeah, it's made of quadrilaterals and triangles, but how do they get it? And basically how they do that is it's done during a process called polygon manipulation. Polygon manipulation basically involves the manipulation of the vertices that make up these quadrilaterals and triangles. And what to do is that they'll take vertices and create more of them and then connect them together and link them together to make these quadrilaterals and triangles. And eventually they'll just work with them enough to a point where it looks like the model that it'll be. And they generally start with something with a basic 3D shape like a sphere or a cube or a cylinder. And let me show you a video of an example of how it's made. So this is a timeline, so it's sped up, and it's not what it looks like in real time.
You can go back to it.
Anyway, so basically, what they'll do is, just to describe what would have been in that video, is that they'll start, for example, with like with a cube, and then for example, to make like a limb, they'll take some of the vertices on one side, 4 of them, and then extend them, and then connect them, and then maybe like make those resulting pair of set of vertices smaller, and then make more of them, and eventually what they'll do with that is they'll just build on those vertices, and by moving them and getting the right shape that they want, it'll start to look like something that you might see in a movie with other things added onto it. But I'll just move on. So, and then the other way that, the other technique that can be used to make 3D models into polygons is known as bumper normal mapping. Bumper normal mapping is basically it uses a picture to as like a template for defining extra detail on a model. And what you think of is you can think of it like using a stamp with ink on it, and having that stamp will have a picture on it, and then we'll just stamp it onto a sheet of paper. And so here's a visual example. So on the left side, you have a perfect sphere, and then right next to it, you have this image, and that's filled with little dots and grains. And each little bit, each pixel of a black color represents an indentation into the sphere on the left. And on the sphere on the right, you can see what the sphere looks like after having that image applied to it. And here's some examples of where it can be used. It's most often used in 3D CGI with either making the pores on the faces, because pores are part of the imperfections of faces, and imperfections are what make a lot of human faces look realistic. Because if they're perfect, then they don't look realistic. Here's another example. Here it's used again on the pores, but it's also used, I don't think you can see it on this projector, but it's also used to make the pores on the suffix polo shirt. Because we all know that polos have little textures in them, and bumper normal mapping can be used to make those. And so the other technique that they can use is called sculpting. Now, sculpting, it works like it sounds. The only difference between sculpting as 3D programs and sculpting in real life is that they use different mediums, essentially. The techniques are all the same. They'll make something by pushing and pulling out something, and but instead of using their hands and working with a real piece of clay, we'll have their 3D models, and they'll just be using a mouse or a stylus. So here's a video of an example. Hopefully this one works.
Also figures.
Yeah.
Oh yeah.
I guess not. Okay. Sorry about that. But basically, what they'll do is they'll start with a basic model that they'll retrieve from polygon manipulation, like I described before, and then they'll use sculpting tools to add on extra detail. And so here's an example. In this example, it was best used to make out the subject's facial structure, especially with this because Kobe Bryant has that kind of trademark style, smile and grin, and he has this. It's a very recognizable facial structure, and it's also used on the left side of his face there to make the veins, and on below the veins that make up the neck. And another example is that it can be used to make cloth as well. It's very good at making modeling cloth and fabrics. And here on this leather suit, you can see the folds, and sculpting is what makes some of those, making those folds look realistic. It's what makes it a lot easier. And it can also be used to make fluids. So like I said before, it's really useful for modeling cloth or fabrics, and this is one of the better examples. And it's most noticeable in the folds of his robe or in the folds of his pants, because otherwise making those through polygon manipulation would be really hard. Sculpting not only makes that easier, but it also allows them to do it well, and so it looks realistic, and it makes it a lot faster. And so I'm not going to even bother with that video working. But basically, the other technique that they can use to do something in 3D is using a 3D scanner. Now, it's not used very often because they're expensive and relatively impractical, but they are still used in some non-creative uses, like in actual industry or making design or something. And what they'll do is they'll basically use, this is a very simplified version of what it actually is, but then basically what they'll do is they'll take a scanner and then scan the subject, and then using that information, put it into a 3D program, and then use that as a 3D model like they would have done for sculpting or polygon manipulation. And so the next part is texturing. Now you can basically think of texture as the process of giving a 3D model skin. And so in that way it's really important, because otherwise they're just like boring gray models. So yeah, they're just images that are basically stretched over the geometry of the 3D model. And there are generally two types of textures. The first type are basically textures that are either scanned or photographed. On the left you have a corrugated steel texture, on the top right you have a brick. And on the bottom, it's like dry cracked ground. And how these might be used, if you have a model that's going to be a shipping container, like say a rectangle, you would basically apply the texture to the side of the shipping container in order to give it some actual coloring patterns to it. And then in the same way with the brick picture, you could use that and apply that to the side of the 3D cube to make it a house. So it looks like it has, like the side of it is made of bricks. And then what they'll also do is use the ground textures to make the ground. Usually the ground in a movie or a game unit is just a flat plane, and they have textures applied to it. And so the other kind of textures that can be made are they're basically either custom made or digitally painted. The ones that are custom made are generally made by hand in Photoshop. And so in the middle here on that picture, you have the three, and then the thing in the middle is what's called the color map. And on the right, and the color map basically is what it'll show as the color of the model. And then on the right, you have what's called a depth map, and that defines how when the subject is lit, how shadows will be cast based on the information on the depth of the model using that depth map. It's kind of a complex topic, so don't get hung over. But here's an example where it can be used. On the bottom right, we have a color map, which, like I said before, gives you the color of it. And then on the middle, on the right, we have the depth map, which, like I said, assigns how shadows will be cast over it. And over here, it's the same thing. Except in the right there, you have the color map, in the middle again, the depth map. And so usually, a lot of the difficulties in texturing can come from how the texture is going to be applied to the 3D model, because it's very important that it's applied in a way so that any parts of it don't look stretched. Because if you've ever seen a globe, sometimes because of the way they unwrapped the world, the Earth, so to speak, Greenland looks like ridiculously large. And so it's important in that way to get it stretched out right and that have everything applied correctly. And that process of doing that is called UV mapping. So UV mapping, so here's an example. So you have a skull. In order to UV map something, you have to define seams along a head, along the vertices of the 3D model. So here they define seams along the back of the model, and then when they unwrapped it, based on those seams, that's where they if you imagine peeling an orange, that's where they kind of started the peeling. Here's another example. Here you have a sphere, and to unwrap this one, they put seams along the equator, and then when they unwrap it, they have two halves of it, and so that way they can just take pictures of the one bottom half and the top half of here, and then just overlay those over the UV map, and then in that way they'll be applied correctly. So next we have materials. Materials basically define how a 3D object will interact with light of the environment. So you can think of it as like the optical properties of something. And so like textures, materials are really important. If you didn't have any materials, they wouldn't be able to interact with the lighting of the scene in any way. And so the three properties of the three main properties of materials are shading, reflections, and subsurface scattering. Shading is basically how shadows are cast on it, and reflections, well, the reflections. And subsurface scattering is more complex, but I'll be talking about it later. So here's an example of what I mean by shading. So here on the left, you have a cube that has no shading applied to it. So when it's rendered, or basically they turn it into an actual picture instead of just having a 3D scene, it doesn't have any shadows on it. And you can't really tell that it's a 3D object. At least not really unless you know what a cube already looks like. And so on the right, this is what it looks like with shading. So now you can actually define the edges of the cube because some parts of it are darker than other because of the way the cube is oriented between itself and the light source. And so you then get shadows that look darker and lighter than others. And so it's important because it defines depth on an object. Without it, we wouldn't have any frame of reference on what the geometry of the model actually is. So we all know what reflections are, but for computers have a lot of different ways that they can make reflections. And the most common method, the method that produces the best reflections as well, and most efficiently, that process is called ray tracing. And it's basically the name of a complicated process that essentially involves tracing the path of light from the light source, and then it defines how it will behave when it hits the object. And like I said, it's complicated and there's a lot of math behind it. But that's all you should take away from it, is that it makes shiny things in the virtual world look like shiny things in the real world. Here we have some glass where they use ray tracing to define the materials of the glass, and so that way they produce realistic reflections. And if you look through it, they also distort the view of if you were looking through glass correctly. Here's another example, except using a card. This is an Aspen Martin. And so to make part of the material of the card, they used ray tracing in order to do it, make it look good. And so subsurface scattering, basically, it's the process that defines how light will interact with objects that have materials, surfaces, that are translucent. So some examples of those are skin, for example. Here, if you have if you're showing the ears are relatively thick and they're all made of just skin and cartilage, and there aren't any bones. And so subsurface scattering, when the artist makes the object and it has subsurface scattering, they'll define the thickness of an object. So that way they know, the computer program, when it renders it knows how the light should appear coming through. And so here, the ears are relatively thin, and so there's a lot of light coming through it. But in the head, you don't see it as much because it's a lot thicker and you have organs and bones in between. And it's also used to, like other objects, not just skin, but things like melts. Anything that's translucent, basically. It's also used in gelatin or even marble, because marble is somewhat translucent to a certain degree. So here on the far right, we have you have glass and melt, but the melt doesn't have anything other than just a basic color map and shading applied to it. And then on the right, you have one type of stuff, one method of doing subsurface scattering, and you can see how it gets basically a little soft. That's the most profound effect of subsurface scattering, is that it makes something look softer. So you can see how that's really important if they want to make a cute character, or even like an animal, look realistic, because otherwise the skin tones just will look like plastic. And here's another example. So here you can see it's most noticeable on the skin, especially on the nose and around the lips. If there was no subsurface scattering applied to it, it basically looked like her skin was made of plastic because it wouldn't have any softness to it. So the next part is animation, and this is the last of the big three. And there are three techniques to animate something. You can do it either by using keyframe animation, using motion capture, or by running physics simulations. And so just to get like a primer so you can understand what I'll be talking about, we all know animation is basically a process to simulate motion by rapidly displaying images one by one in order to create the illusion of motion. Now, so what they'll usually do with the traditional two-dimensional hand-drawn animation, they'll basically draw their character in a slightly different position And then when they put those all together and show it rapidly, it looks like it's moving. And so here is an example of what I'm talking about. So in the first frame, you have a ball, and it's slightly squished, and then the next it's not, and then the next it's in the air, and the next it's coming down, and then it lands. And so when these are shown side by side rapidly, it looks like a bouncing ball. However, though, with 3D animation, it's not really practical to redraw your character or make your character again once after the other. And so to fix this and to make it easier, they have this system of controlling a character that's called rigging. Now, rigging basically allows them to manipulate a 3D model by assigning a group of vertices, and like I said before, vertices are what make up a 3D model. So for example, if they wanted to control the hand at once, they would take all the vertices that apply to the hand and then assign them to an object called the bone. And the bone is just a term for the entity that will then control the hand with the bone. And then if they wanted to get more detailed, they'll create separate bones for the hands, make up things like the fingers. And if they want to go even more in depth, they'll create different bones for each part of the finger. And so then by assigning vertices to bones, they can now just control these bones instead of having to control hundreds or even tens of vertices. And so this makes the job a lot easier. And so now using this rigging system, an animator can utilize a method of animation called keyframe animation. And what keyframe animation is, well, it basically relies on, in order to draw something, the object has to be redrawn every time to make it look fluid. And so traditionally that becomes a problem because then they have to redraw for every time. But with keyframe animation, once you can do that, if you wanted to say animate something moving from like a position called, let's call it point A, and then another position called point B, what they can do is just set, they'll have the ball at point A, and then they can define the start key, which basically defines the start of the animation, and then move it to the next position, and then define the end key, which defines the end of the animation. And so then with that information, the computer can just fill in the gaps, and it'll look like when they show the animation, it'll look like it's just moving in between. So in that way, an animator, if they want to move something, they only have to define the start and end keys. And there are also, it's important to know that also there are more than just the start, there are like 3 types of keys. The one I described is a position key because it will define the object's position in an animation. They also have scalar keys, which define the size of an object, and also the rotation key, because if we're animating a lot of things, you need to animate like the rotation of something like a knee joint if they're walking. So let's move on. So the next method is called motion capture. Motion capture basically involves recording the movements of an actor by placing these markers along as many parts of their body as they can. And then using a video camera, they can just record the motion of the markers in order to record the motion of the actors. And so basically what this allows them to do is then that they can take an active performance, and then they can basically transfer it into their computer program and basically take the performance from the actor and put it into and use it as like animation information for a 3D model or 3D character. And so this is it's been used really well, relatively recently, like in the past 10 years with movies such as Lord of the Rings or Avatar or Rise of the Planet of the Apes. In Lord of the Rings, they used Gollum. His animation was mostly made, not entirely, using motion capture. They had an actor dressed up in a suit, and then they had these markers, and then using video cameras they recorded the movement of the markers to get to record his motion, and they put that into their 3D model of Gollum, and then they just use that as the animation. And that's one of the reasons why Gollum looks so realistic in his movements and also his facial expressions. And here's a video, which is a shame that it won't work because it's a clip from the behind the scenes of Rise of the Planet of the Apes using the same actor that they used in Lord of the Rings to make the animations for Caesar, who's the main character. And basically, what was in there is that I was trying to show you how they had an actor basically set up with the markers, and the markers are generally just like bright green dots of paint that they put along the actor's face. And then with a camera mounted on his head and placed in front of him, the camera records the motion of those markers, and then they can use that to animate the face of the 3D character. And so the other technique that can use, they'll use physics simulations. And basically they only use this when they need to animate scenes where they have like hundreds or like thousands or like hundreds of thousands of objects on screen moving. Because otherwise, if they were trying to animate every single thing, it would take way too long, and it just wouldn't be practical. So what they do is that they'll basically define the properties of something that they're trying to model. They can you can have different properties such as you can define that it's just like a hard object, like a piece of dirt or like a pellet of something, or it could be water, or it could be a fabric, like just cloth, or different types of cloth, like leather. And all of those different materials will have different properties based on how they are known to act physically in the real world. And so, in movies where there are a lot of explosions, or even where they have characters who are completely CG animated, and they have fabric material on them, they'll use physics simulations to calculate and accurately demonstrate the animation and movement of those objects. So in movies like 2012 or Transformers, where they have a lot of explosions, or 2012 they had a tsunami running through, they use physics simulations to calculate the movement of that water and make it look realistic. And we can't see that. And we can't see that. We can't see that.
And then turn your internet off.
And yeah, it's not that important. But anyway, we'll move on. So the next part is lighting. And so lighting, it's basically not too different from lighting in real situations, because generally any of the other parts of computer generated imaging, it's just as important, because if you don't have a well-lit scene, even if you model the most incredible thing, it just won't look good with proper lighting. And so the only difference with lights and CGI is that with lights and CGI, you can have them do things that are just generally impossible in the real world, like defining whether or not they will cast shadows on objects that they shine at, or you can also just have tons of lights that you just couldn't practically buy or power in a regular scene. And so the next part is compositing, and there are generally two common parts to compositing. Those can be simplified as assembly and enhancement. And assembly just involves basically, if you have a scene where you have a lot of objects in, but they're not generally the same, they're in the foreground and the background, you're going to end up compositing something, because you're not going to make everything in just one scene. You're going to do everything individually, and then right before you render, you're going to bring everything together. So let's say you're trying to animate something where you have characters in front of the mountain, and you have this mountain range in the background. You would model, texture, and animate the characters in the foreground, and then in compositing, you would add in the picture of a background that you had in the picture of sky to make it look realistic. And then what you would do, and then you can also insert things that you would normally have, the physics results from a physics simulation, or just particle effects too, which you would get from the physics simulations. And so the other part is enhancement. Enhancement will just it sounds, it'll enhance three things about a scene. And that generally is lighting, color, and details. And so with lighting, we'll be adjusting the contrast or adding depth of field to an object, which basically will artificially make it look like the camera, virtual camera is focusing on something else. With color, there would be adjusting things like the brightness of a color, the tone of the color, and saturation, or how deep a color feels. It's kind of hard to describe. And then on the detail side, what they might be doing is most commonly they'll be sharpening something, or to make edges and details on the model look more profound. They'll have to stand out. Can't show you that. And so the last final step is rendering. And rendering is basically they'll take the information from their 3D scene, and right now that's just in the form of data, and then it's shown kind of prematurely as the basic models, or the basic versions of what they're making. And then the process of rendering will just take those, and then the computer will calculate how it's supposed to look based on what you put into them, like lighting, what the materials are, and then turn out a final scene that you would see in the movie or 3D still. And so generally there are two types of ways that they can render something. They can render it using a physical renderer, which will take away from real life the laws of physics and how something should be lit, animated. The problem with that though is that it'll take a lot longer to do it. And then the other way is using ray tracing to do the same thing, which like I mentioned, ray tracing it doesn't follow it doesn't simulate lights realistically, not entirely. And so here's an example of what I mean by like how it looks like when it's rendered and when it's not. On the right side, you have the wireframe view, which basically just views the edges of the polygons that it's made up of, and through the view of the camera. And so that's on the right. And then on the left, you have the final rendered scene. And here you can see you have the final model, its texture, it has its materials applied, and everything looks good. And then also in the background, they composited it, and during the assembly stage, the background of the moon. And then they overlaid certain things like the Life magazine logo, and then like text. And so that actually is a computer-generated still as well. And generally what they'll use to render something, if it's very complex, if they have a lot to render, they'll use what's called the render farm. And the render farm is basically a bunch of computers connected together, all working together on one thing. And so here, this is a frame from inside Pixar's render farm. Naturally, they have their own in-house render farm to do everything. And I'm sure you've probably heard they need this kind of computing power because even with this stuff, it takes 16 hours to render a single picture out of the millions that make up a full-length motion picture. And this is just another picture of it, but from another side. And so each set of lights there is a computer. It's a server, and they're all stacked together in their cases along stands, and then controlled by one computer to render a single frame or something. And so I would have liked to end on this video that I showed you, but because I think it's really important, I'm just going to go out this and try and get it up on YouTube. So this was made by the same artist that made that video that I showed you at the beginning, and it's a commercial for a company that makes countertops and whatnot. Just to end, I hope you enjoyed my presentation, and I also hope that afterwards, now, when you watch a movie with some CGI on it, that you'll be able to at least be able to understand how they made it, and at least have a basic idea, and then with that, be able to appreciate it. Thank you.